Hi, and welcome back to Carbohydrates. We are officially starting the polysaccharide portion of our carbohydrate world land that we are in. So we did monosaccharides. The most famous of all monosaccharides is glucose. Put a couple monosaccharides together and then you get yourself a disaccharide. So that leads us into the next step, which is polysaccharides. So here we go. Big letter C in your notes is polysaccharides. Polysaccharides, change ink here really quick. Polysaccharides is essentially when you get a few hundred to a few thousand monosaccharides joined together. So you can imagine if we had our disaccharide linked together with a glycosidic linkage, if we did a bajillion dehydration reactions, you could eventually make this huge, long carbohydrate chain, if you will. And that's exactly what a polysaccharide is. So polysaccharides, a few hundred to a few thousand monosaccharides linked together with glycosidic linkages via dehydration reactions. A few hundred to a few thousand monosaccharides linked together by glycosidic linkages via dehydration reactions. All right. Now, there are two main types of polysaccharides that we need to study. The first are storage polysaccharides, and the second will be structural. So let's talk about storage polysaccharides right now. I'm going to erase this definition so we have all the room. So polysaccharides, one last time, a few hundred to a few thousand monosaccharides linked together by glycosidic linkages via dehydration reactions. So let's talk about storage polysaccharides. Now, all of these carbohydrates are residing inside cells, whether they be plant cells or animal cells. We're going to talk about both of those. Now remember, the cell is the structural unit of any organism. You are made of billions and billions of cells, and those cells take shapes into different tissues and then in different organs and ultimately create the whole organism. Same thing with a plant. They have different tissues and then they create the whole organism as well. So when we think about these things, think about them residing within a cell so that cell can do its job. And that's why we have to learn about macromolecules, because they are the building blocks of the cell, if you will. So, number one, under polysaccharides, these are the storage polysaccharides. And some of these words are going to be very familiar to you. Storage polysaccharides. These are polysaccharides stored in cells, and they are broken down later for energy. So if I'm a polysaccharide, I'm a polymer, and I need to be broken down, what kind of reaction breaks down polymers? Hydrolysis reactions. So if a hydrolysis reaction reacts to separate my polysaccharide, I'm going to create a bunch of monosaccharides. And then those monosaccharides can be used as energy. So what you need to know for storage polysaccharides, these are polysaccharides stored inside cells, stored in cells for energy use. And what you need to know is that hydrolysis reactions break apart the polysaccharides into monosaccharides that can be used for energy. So hydrolysis reactions break apart the polysaccharide into monosaccharides that can be used for energy. there's two kinds of storage polysaccharides that we need to learn about. One happens in a plant cell, the other one happens in an animal cell, such as us. So when I say animal cell, I mean any animal. So that could be your cat, dog, us as well. So here we go. So storage polysaccharides, little a under storage polysaccharide. The first one we're going to talk about is starch. Starch you've heard of before. You eat starchy foods sometimes. If you think of a potato, nothing but starch in there. So starch, these are polysaccharides found in plant cells. A potato is plant, right? So these are storage polysaccharides in plant cells. Now here's what you need to know about starch. Starch is really, 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 really long. So there's many, we're going to go back to glucose, many glucose monomers linked together to form starch. And what you need to know under starch, basically starch is hundreds of glucose monomers linked together with 1,4 glycosidic linkages, and essentially when you start creating a very long glucose chain, the chain starts to spiral into something we call an alpha helix. That's just the normal nomenclature we use for a spiraled shape in organic chemistry and biochemistry as well. Whenever you see a spiral, it's called a helix. Depending on what direction it's going, it could be alpha or beta. It's kind of neat. So starch, this is hundreds of glucose monomers linked via 1,4 glycosidic linkages. And what you need to know, it forms an alpha helix. That's the Greek symbol alpha for alpha. It's Greek A. Now I'm going to erase all this on top so you can see what starch looks like. I'm going to do a shorthand version of glucose. Instead of drawing all the different functional groups on it, I'm just going to draw the carbon skeleton with the oxygen for the glycosidic linkage. Makes it a whole lot easier. So if that's one glucose monomer, and I'm linked together with another one, you can start to see how these 1,4 glycosidic linkages work. And keep going on and on and on and on. So here's glucose monomer after glucose monomer. That's carbon number 1, carbon number 4. There's my glycosidic linkage right there. So if you imagine hundreds of these all along the way, what eventually starts to happen is the way that these this linkage is actually happening. If I'm the oxygen and I'm holding a glucose here and I'm holding a glucose here, I'm not holding it next to me side by side. I'm actually kind of tilting it a little bit. So as I start chaining over and over and over again, I start to create this really neat looking alpha helix structure like this. It just slowly starts to turn. So if this would be glucose, 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 and in between are all the linkages. So pretend that every little dot that I'm drawing here is a glucose. That's what starch would look like. So it's kind of nice because you can imagine as you coil something around, you can actually create a more compact structure so you can store a lot more sugar in a structure if you wanted to. If it was one long chain, it wouldn't pack as well. So this allows it to be a more compact structure as well. And every time you want to do a hydrolysis reaction, so if the plant, for whatever reason, needs energy, because plants need energy as well, if the plant needed some energy, it's going to need some glucose quick. It'll do a hydrolysis reaction, boom, cut it off right there, then this glucose can go away and do some energy, whatever it needs to do to help create energy actually. All right, so that's starch. Starch, storage polysaccharide in plants. So, in plant cells. The other thing you need to know about starch is where starch is found. If you look inside a plant cell, it's inside this compartment, an organelle, we call these, a compartment called a plastid. You don't really need to know about what it looks like or what it is, but I want you to know that word because that's something that may come up somewhere. So what you need to know is starch is found in compartments, and those compartments are called organelles. We're going to talk a whole lot about organelles in the next unit or two when we get to cells. So found in compartments, organelles, called plastids. There you go. And that's all you need to know for starch. Storage polysaccharide in plants, lots of 1,4-glycosidic linkages, forms an alpha helix, found in plastids. All right, next one, little b. This is going to be the storage polysaccharide in animal cells. This one's a little bit different, but very similar. You can see over time as we study these macromolecules that you literally are what you eat. So this is going to be little b. This is the storage polysaccharide in animal cells, and this one is called glycogen. Storage polysaccharide in animal cells. Okay, so glycogen resembles starch a lot, but glycogen has a different shape compared to it. We probably need a little bit more energy inside our cells than plants do. They also get energy that they have the whole photosynthesis going on for them as well. So we need to utilize our energy a little bit differently than they do. But what you need to know for glycogen is, like starch, it's made of a bunch of glucose monomers linked together with 1,4-glycosidic linkages as well. But it's made of branching alpha helices. So we get a little bit more bang for our buck in this if you go with that. So also made of glucose monomers, same 1,4-glycosidic linkage, and what you need to know, it creates a branching alpha helix. And here's what that would look like. You would have all your 1,4-glycosidic linkages, and you would have an alpha helix, just like starch, but it also branches all over the place. I not make up, that's pretty, but that's what glycogen would look like. It's just very extensively branched. So imagine how much more glucose you're getting inside glycogen as well. What you need to know is that glucose is stored inside small little granules within your cells, especially within your liver and your muscle cells. If you think about it, your muscles need energy to move. So you need a source of energy in the form of glucose. So remember, there's glucose monomers all over the place here. I need to be able to do hydrolysis reactions constantly to essentially burn up that sugar, if you will, to turn it into energy. And your muscles do that daily. Typically, within a normal day, if you're active enough, you will use up all your glycogen storage in one day. You replenish it with your diet. So even if you're on a low-carb diet, you still probably get enough to use all your glycogen storage every day. Even if you're on a high-carb diet, you may not use it all the time. And so it just stays there in storage if you don't use it. So I'm going to put a little number 2 over here because I'm out of space over there. But what you need to know is that glycogen is stored, we call them granules. They're just small structures within the cell. They're not even the organelles. So in granules, in liver and muscle cell. So, outside of your muscles, your liver is working nonstop as well. Your heart is too, but it's a different kind of muscle. It's cardiac muscle, not the striated muscle that you see in your muscle. your skeletal muscle. So your liver is constantly replenishing itself, doing a whole bunch of functions, so we need some quick energy in there as well. So glycogen is stored in granules in liver and muscle cell. So as your demand for energy rises, so say you decided to go take a quick sprint across the street, you're going to be burning up some glycogen really fast. After you eat a meal, you convert all the sugar that you're eating and you create all the glucose monomers basically conglomerate together to form a lovely glycogen structure, and you store that for later use. There's a hormone that allows that storage to happen, and that's insulin. So if you know anyone who's diabetic, or if you're diabetic, if you don't create that insulin, that sugar stays in your bloodstream, and you actually need to get it out of your bloodstream and store it for when you actually need it. So insulin helps store your sugar, and there's another hormone called glucagon which releases your sugar, and that is where glycogen gets taken apart to use your sugar. So these hormones work together to do all that. So you really do use all your glycogen storage in one day if you're active enough. So these are your storage polysaccharides. Come back, we're going to talk about your structural polysaccharides. We only got 2 and they're pretty quick, and then we'll be done with carbohydrates and we'll move on to lipids. See you soon.